Okay, so for the theory portion of principle of recursive definition, I'll just solve theorem 8.4, and the solution of that would essentially cover everything in the chapter, right? Okay, so let A be a set, let A not be a member of the set, let rho be a function of functions, so it maps every function on the set of integers, section of integers, and maps it to a unique element in A, right? So in no, I'm not writing. Yeah, so that's what the function rho is, and there exists a unique function h from z plus to a such that h of 1 is equal to a naught, hence why we had to choose a member, and h of I is equal to rho of h restricted to uh, section till I minus 1 for I greater than 1, right? Yeah. So h of 2 would be h restricted to 1, right? So it will be based on h1. Yeah. Yeah, that's it. Okay. That's the theorem. Now, so first, let us show that there is a, yeah. So first, let's show that there is a function that for every section of integers, there's a function from 1 comma 1 till n till a, right? And we'll show this by induction. So h of 1 certainly exists because, by the hypothesis. Yeah, so H1 exists by hypothesis. So, I mean, H1 is defined. So H from restricted to 1, or H as a, hang on, H as a function from singleton 1 to A is a function and it exists. So now let's assume H is defined from 1 till n minus 1, or n, whatever you want, till A, right? Now we have to show that there is a function that's from 1 till n till A, right? Okay. And for that, we'll just take this function and add on to it the coordinate n comma rho of h, this one. So this function is going to give us a unique value of a by the assumption hypothesis, and we're going to add it to h prime. And this is our precise function from the section n plus 1, section of n plus 1. So yeah, the inductive step is true. So by induction, we have a function for every section of integers till a. Okay. Now, the trick is essentially that to define the function from z plus to a, we take the union of all such functions. But to make sure we can take the union, we need to ensure that we actually get a function from taking the union of the rules. And for that, we need to ensure that for any two functions that have the same domain, have an overlapping domain, their value in that domain is the same, right? Otherwise, we'll have two different values, and h of m is equal to a, is equal to b, and a is not equal to b. Contradiction. And that's why we can't have a function. So for that, we have to make sure that there's a sort of uniqueness for every function we define. And that's precisely what we're proving next. So let h be from a section 1 till m to a, and let h prime be from 1 till n to a, right? Now, and without loss of generality, let m be less than n or equal to. If they're equal, we just have to show that they're equal. Yeah. Okay. So let uh, p be the least number such that h is not equal to h prime, because if h of p because by the well-ordering principle, if we take set of all p such that they're not equal, there has to be a least number, right? But h of p here is satisfying the property, so it's going to be defined as what row of h restricted to hang on, 1 till p minus 1, and that's equal to h prime p for the same reason. So that's a contradiction because this function gives a unique one. So if this function gives a unique value, why are they different? And that's the argument to show that in the common domain they're going to be, right? So because of that, the common domains are equal, and therefore we can take the union, and we'll get a function and not any nonsense where we're getting two values. So that's one thing. Now we have to show the uniqueness of the function, and for that, let h and h prime be two different functions so that they satisfy the property. If the exact same proof, let p be the least number so that they're unequal, because at the end of the day, it's still a subset of the integers. And yeah, we'll get the same contradiction, the exact same proof. Yeah.